Welcome, curious minds, to the Deep Dive. Today we're plunging into a topic that's not just reshaping our industries, but quietly transforming our daily lives too. Automation and robotics. You've shared some truly fascinating material with us, and our mission, well, as always, it's to navigate through these insights, pull out the most important nuggets of knowledge, and help you truly grasp the profound shifts happening in this rapidly evolving field.
Absolutely. And we're talking about, the incredible convergence of physical machines and intelligent systems. We'll explore not just how they're designed and controlled, but also the surprising, far-reaching impact they have across nearly every sector you can imagine. Get ready for some serious aha moments that might just change how you view the machines around you.
Okay, let's unpack this then. It's a huge topic for sure, but we'll try and tackle it systematically. We'll start at the very beginning, understanding what truly defines a robot, then maybe move through the core concepts of automation itself. From there, we'll explore the surprising range of tasks robots can perform, peek inside their mechanical bodies, see how they're actually put together. We'll unravel the sophisticated control systems that make them move with such precision, understand the raw power behind things like hydraulic systems, delve into how robots understand their own movements, in-space kinematics, right?
Yeah.
And finally, look at how they sense the world around them and the increasingly crucial role artificial intelligence plays in making them truly intelligent, maybe even autonomous.
The foundation, what is a robot?
So let's kick things off with the fundamental question.
Yeah.
When we talk about a robot, especially an industrial robot, what are we really talking about? What's its essential purpose? What makes it different from just any other machine?
That's a great place to start. Yeah, because the term robot, well, it conjures up so many different images, doesn't it? At its core, an industrial robot is a highly versatile, programmable machine. It's designed with certain, you could say, human-like characteristics. The most classic and apparent of these is definitely its arm, or manipulator. It sort of mimics the reach and dexterity of a human arm. And this arm, combined with its inherent programmability, makes it incredibly suitable for all sorts of diverse production tasks. It's not just doing one fixed thing. It can learn and repeat many different actions.
Right, so it's not simply a machine. It's specifically a programmable machine.
Yeah.
And has this very adaptable form factor, this arm. What kind of tasks does that adaptability really unlock, say, in a manufacturing or industrial setting?
Exactly. Think about the backbone of modern manufacturing, right? Tasks like machine loading and unloading parts, precisely spot welding car chassis, spray painting products with perfect uniformity or intricate assembly work. The key insight here, I think, is its ability to be programmed to perform a specific sequence of mechanical motions, and then crucially to repeat that exact sequence endlessly, tirelessly, and with incredible consistency. This repetition, this unwavering precision, that's a huge part of its value. It frees human workers from jobs that might be dangerous or tedious or just physically demanding.
And these manipulators, these arms that are so central to the robot's function, how are they physically structured? How do they achieve that incredible range of movement and precision?
Okay, so a manipulator is fundamentally comprised of a series of rigid bodies we call links, which are connected by joints. These links and joints, they work together in a kind of coordinated dance. The goal is to position and orient the end of the manipulator, which could be a gripper, a welding torch, a paint sprayer, you name it, any specialized tool relative to its base. It's fascinating because a robot joint functions very, very similarly to a human body joint. It provides relative movement between two parts. Just like, say, your elbow allows your forearm to rotate relative to your upper arm, a robot joint allows two links to move relative to each other. Most industrial robots typically have maybe 5 or 6 such joints, and these are categorized as either linear, meaning they slide, or rotating, like a hinge. That gives them the flexibility needed for a vast array of tasks. The controllers then orchestrate these joints, coordinating them to execute the work cycle, seamlessly.
That makes perfect sense. And computers, where do computers fit into this picture? I mean, I imagine they're absolutely central to making all this intricate movement and programmability actually happen.
Oh, absolutely central. Computers aren't just integral. They are the very brain of modern robotics. Modern industrial robots, much like other advanced manufacturing systems, are sophisticated automation systems that rely entirely on computers for control. And it's not just about a single robot anymore. Computers now run entire production lines, orchestrating dozens, maybe even hundreds of machines. They control standalone manufacturing setups too, like machine tools that precisely cut metal, welders that join components, inspection systems ensuring quality, laser beam cutters etching designs with microscopic accuracy. What's truly fascinating, I think, is that even more advanced robots, often driven by AI, are enabling full factory automation. The whole manufacturing process, from raw material coming in to the finished product going out, can be orchestrated and controlled digitally, often with minimal human intervention needed on the floor. It's like a digital symphony of production, really.
Unpacking automation types and concepts.
Okay, that leads us perfectly into the bigger idea of automation itself. It's a word we hear all the time, but where does it even come from? What does it truly signify beyond just, machines doing things?
Yeah, the word automation itself actually originates from Greek. You've got auto, meaning self, and matos, meaning moving. So literally it's about a setup that proceeds by itself, a self-moving system. But beyond that original sort of etymological sense, the core insight is that automated systems generally achieve performance that is far superior to manual systems. We're talking in terms of power, precision, speed. It's not just about doing it themselves, it's about doing it better, often way beyond human physical capabilities. Think of it not just as replacement, but as a transformation of what's even possible.
Okay. So it's about exceeding human capability, not just replicating it. How do we formally define automation then? And are there different kinds? Do they serve different purposes in the industrial world?
Right. Formally, automation is defined as a collection of technologies that lead to the operation of machines and systems without significant human intervention, achieving performance superior to manual operation. And yes, it's generally divided into two main types, reflecting different production needs and, crucially, different production volumes. First, there's fixed automation. This type is used when your production volume is huge, really large. It makes it practical and economically viable to design highly specialized equipment just for that one product, for high-rate, low-cost processing. A classic example is the auto industry, right, where incredibly integrated transfer lines are used for precision machining on engine blocks or transmission components. Imagine a dedicated path, like a highway built for only one type of car. Every step is optimized for that specific product. Once it's set up, it's incredibly efficient for that single purpose, but, and this is key, it's notoriously difficult and expensive to change if you want to make something else. Then the second type is flexible automation. This is more suitable for mid-volume production ranges, where you need to produce a variety of different products, but maybe not in those astronomical quantities. It typically consists of a series of workstations, interconnected by sophisticated material handling systems, maybe storage equipment too. These systems are designed with computer control that allows them to process distinct product configurations simultaneously. And they can control entire manufacturing systems, like flexible manufacturing systems, FMS, or even computer integrated manufacturing, CIM. So while fixed automation is like that single-purpose superhighway, flexible automation is more like a highly adaptable railway network. It can route and change tracks for different types of cargo, giving you the agility to switch between products fairly quickly without massive retooling costs.
That distinction makes a lot of sense, the dedicated assembly line versus something that can adapt. Now, within robotics itself, you mentioned there's this critical distinction between autonomous and traditional robots. Can you walk us through what really sets them apart? Because I imagine it's about more than just, the hardware.
You're absolutely right. The difference is profound. It really lies in their intelligence and adaptability. It marks a significant evolution in what robots can do. Let's start with traditional industrial robots. These are the workhorses you typically see on factory floors, the absolute masters of repetition. They primarily use robot arms with motions that are largely pre-computed, very planned out. Programming is often done using a teach box or pendant, where a human physically guides the robot through a sequence of points that it then just memorizes. They excel at repetitive tasks, offering high speed and incredible precision because their actions are rigidly defined, and they operate in a predictable, controlled environment. They typically have few, if any, sensing operations. They just operate with pre-planned trajectories and task policies with little to no interaction with humans during operation once they're running. Think of them as maybe virtuoso musicians who can play one piece perfectly, flawlessly every single time, but really struggle if you ask them to improvise or react to something unexpected. Now, autonomous robots, these are designed quite differently. They're built to adapt and react. Their control involves multiple complex subtasks. This includes understanding and modeling their own structure, their kinematics, how they move their dynamics, forces and motion, and even odometry. That's essentially figuring out how far they've traveled and in what direction, based on their own internal sensors. They feature reliable control of their actuators and inherently operate with closed-loop control. That means they're constantly adjusting based on real-time feedback from their environment and internal state. Key capabilities include dynamically generating task-specific motions on the fly, sophisticated path planning to navigate complex, maybe even changing environments, and the deep integration of various sensors to perceive their surroundings in real time. What's truly impressive is their ability to cope with noise and uncertainty. Things like filtering out noisy sensor readings or dealing with slight inaccuracies in their actuators. And they can create flexible control policies to deal with completely new situations or unexpected changes they encounter. They're more like the improvisational jazz musicians, able to react to unexpected cues and adapt their performance dynamically.
Okay, so it sounds like traditional robots are masters of consistency within a very defined box, while autonomous robots are designed to adapt, learn, and react to the unpredictable world outside that box. So, where do we actually see these machines, both the masters of repetition and their more flexible cousins? Where are they used in the real world?
Where do robots work? Applications of robotics.
All right, the applications are incredibly vast now, and they're driven by a pretty compelling set of factors that often intersect with, well, human limitations of preferences. We typically see robots deployed where there's a clear need to replace human labor, primarily due to factors like dangerous work environments, situations that are just plain unsafe or unhealthy for people. Think handling hazardous materials, working in extreme heat or cold, or in environments with toxic fumes. Repetitive, boring, or maybe just annoying tasks. Jobs that cause human fatigue lead to mistakes or are simply not stimulating. Things like endlessly inserting tiny components or stacking boxes all day long. Multi-shift operations. This is a big one. Robots can work continuously without breaks 24/7 across multiple shifts. That vastly increases overall productivity and how much you get out of expensive equipment. Infrequent transitions. Tasks that don't change very often. This allows for long, consistent runs where reprogramming isn't a constant headache, maximizing efficiency. Need for a steady pace. Maintaining a uniform production speed is often critical for downstream processes. Robots ensure consistent output and help meet production quotas reliably, operating for extensive hours without rest. They perform uninterrupted work cycles, unlike human workers who obviously need breaks, rest, recovery time, automated operations, responding consistently and predictably to automated commands within a larger interconnected system. This ensures seamless integration. And finally, minimizing variation, ensuring consistent quality and process control. This significantly reduces human error and improves product uniformity, which is crucial for quality.
So it really boils down to safety, efficiency, and that unwavering consistency. How are these diverse applications typically categorized? Is there a structure to how we think about what robots do?
Yeah, we can broadly divide industrial robot applications into 4 main areas, each addressing a critical need in production or logistics. First, material handling applications. These are all about moving materials or parts from one location to another. It sounds simple, but it's fundamental. Within this category, find several common tasks. Part placement. This is probably the most basic, but also the most common. The pick and place action. It often uses simpler, maybe lower technology robots, frequently powered by pneumatics. They might only have 2, 3, or 4 joints. Think of a robot arm precisely grabbing a component from a feeder tray and placing it onto an assembly line. It's ideal for rapid, repetitive transfers. Palletizing and depalletizing. This involves stacking parts onto a pallet that's palletizing, or conversely, unstacking parts from a pallet one by one, depalletizing. Imagine a robot taking finished goods off a line and perfectly stacking them onto a shipping pallet, optimizing space, ensuring stability. Or the reverse, feeding parts from a pallet into a machine loading and unloading. Here, a robot either loads components into a production machine, maybe the unloading happens some other way, for instance. A robot feeds sheet metal into a press, but the finished parts just drop out by gravity. Or the robot unloads parts where raw materials were loaded manually, like in die casting or injection molding. The most complex case is when the robot does both, loading raw materials and unloading finished parts. A common challenge here is synchronizing the robot's cycle time with the machine's cycle time to avoid bottlenecks. It needs careful planning, stacking, and insertion operations. In stacking, the robot places flat parts on top of each other, where the vertical drop-off position has to change regularly as the stack gets higher. In insertion, the robot precisely inserts components into, say, the compartments of a divided carton, or maybe into a testing fixture. Expert speaker. Now, for material handling, a robot needs certain features. Its manipulator has to safely lift the components, right? It needs sufficient reach to cover the workspace. Often, a cylindrical coordinate-type robot is good here because of its rotational and vertical range. Critically, its controller needs enough memory to store the entire program sequence so it can move efficiently between points, and it needs the necessary speed to meet the required transfer cycle time. Second main area, processing operations. In this case, the robot isn't just moving things around, it actually manipulates a special process tool as its end effector to perform a direct operation on a workpiece. This includes vital industrial applications like precisely controlled arc welding or spot welding, machining parts, riveting panels together, applying spray paint with perfect uniformity, metal cutting, deburring rough edges, or polishing surfaces to a mirror finish. Here, the robot is the tool, executing the process with that crucial consistency. Third, assembly applications. These usually involve intricate part handling manipulations, sometimes the delicate use of special tools, and other automated tasks needed for putting components together. This is where precision, careful sequencing, and often some degree of sensing are really paramount. It enables robots to build everything from tiny electronics to massive aircraft engines. And finally, fourth, inspection operations. These require the robot to accurately position a work part for an inspection device, like holding it up to a camera, or alternatively, to manipulate an inspection device or sensor itself to conduct the inspection, maybe moving a probe over a surface. This ensures quality control, checks dimensional accuracy, detects defects, making robots a critical part of maintaining high product standards.
That's a truly comprehensive overview of what robots do across the industrial landscape. It's amazing how diverse it is. But to accomplish these tasks, sometimes incredibly delicate ones, they need a highly specialized physical structure. Let's talk about the actual body of a robot. How are they built?
The body of a robot basic structure.
Right. So at a fundamental level, what actually defines a robot's physical body and how it interacts with its environment? Well, a robot is essentially a machine capable of physical motion specifically for interacting with its surroundings. This physical interaction, it could involve locomotion, moving from place to place like a mobile robot, or manipulation of objects like an arm, or really any other task that changes its own state or the state of its environment. And to perform these tasks, a robot has a specific structure made up of interconnected parts.
And this structure is made up of links and joints, as you mentioned earlier. Can you elaborate a bit more on what you mean by joint primitives and how they combine to form these serial linkages?
Yes, exactly. A robot structure is fundamentally a multi-body system. You have multiple rigid bodies, which we call links, connected together to form a linkage. And the way these links connect, the joints, that defines the robot's basic motion capabilities. There are really two primary types of connections, or primitive joints, that are the building blocks for almost all robot arms and legs. First, you have a prismatic joint. In this case, a pair of links makes a translational displacement along a fixed axis. So basically, one link slides linearly on the other in a straight line. Think of a drawer pulling out from a cabinet, or a piston moving in a cylinder. It's sometimes called an accelerating sliding joint, and it allows for extension and retraction. The second primitive is a revolute joint. Here, a pair of links rotates about a fixed axis. This type is often called a hinge or an articulated joint or a rotational joint. It's very much like a door hinge or your elbow or maybe a rotating turntable. It allows for angular motion. Now, by merging and combining these two primitive joint types, we can create all sorts of useful structures for robot manipulation and locomotion. The most common way is by forming serial linkages, where links are connected end to end, one after the other, just like the bones in your arm, upper arm, elbow joint, forearm, wrist joint, hand. This builds up an arm or a leg segment by segment, creating a chain of motion.
That's very clear. Now, you mentioned that a prime requirement for a robot is to locate its end effector. That's the gripper or tool at the very end of its arm in 3D space. Do robot mechanisms often mimic common coordinate systems to achieve this positioning, maybe more elegantly?
Precisely. That's a really brilliant design principle, actually. If a robot's kinematic structure, its arrangement of links and joints, is analogous to a familiar coordinate system, it can fulfill this positioning requirement quite elegantly. It makes it easier to program and predict its movements because we already understand the math of those coordinate spaces. There are three classic examples that directly relate to these systems. The Cartesian coordinate robot. This robot has three prismatic joints, one for each axis X, Y, and Z. This configuration allows for movement along perfectly straight lines in three-dimensional space. Think of it like moving precisely along a grid. It makes them ideal for tasks requiring linear precision, like picking items from a grid of shelves, or operating a CNC machine, or 3D printing. The cylindrical robot. This one combines one revolute joint for rotation around a central vertical axis, with two prismatic joints for radial movement, in and out from the center, and vertical movement up and down. Its movements map directly to R, theta, and Z coordinates in a cylindrical system. This makes it suitable for reaching objects within a cylindrical workspace, like servicing machines arranged in a circle. And finally, the spherical robot. This one features two revolute joints for angular movement. Think of sweeping motions up, down, and around, like latitude and longitude, and one prismatic joint for radial extension, reaching in and out. These movements directly represent r, theta, and phi coordinates in a spherical system, creating a spherical workspace. It's excellent for tasks like welding large, complex curved structures, where you need that kind of sweeping reach.
But surely not all robots fit neatly into these coordinate system analogies, do they? What are some other important kinematic structures, ones that allow for maybe different types of movement or are better suited for specific applications?
You're absolutely right. While those coordinate system analogies are super helpful for understanding basic movement types, there are other very effective kinematic structures that don't neatly align with them but are absolutely vital for certain applications. One key example is the SCARA robot. SCARA stands for Selective Compliance Assembly Robot Arm. It typically has two revolute joints that allow for horizontal movement, like reaching across a table, and one prismatic joint for vertical movement, straight up and down. It's particularly useful for assembly automation because it offers a broad workspace horizontally and an independent vertical axis. Its selective compliance is the clever part. It's designed to be very rigid vertically, but slightly flexible or compliant horizontally. This is ideal for rapidly inserting parts precisely into holes, as it can accommodate minor misalignments horizontally without jamming, while maintaining vertical accuracy. Then there's the articulated robot, often just called an elbow robot. This is perhaps the most common and versatile type we see today. It consists of all three revolute joints, much like a human arm with a shoulder, elbow, and wrist. This configuration provides a great degree of flexibility and dexterity, making it the standard structure for many robot manipulators. It has that human-like reach and the ability to navigate around obstacles effectively. It can reach almost any point within its large, often spherical workspace. And there's another fascinating kinematic mechanism, also with three revolute joints, but with unique mass balancing structure. This design cleverly incorporates counterweights, often at the elbow joint, which effectively remove the gravity load for all three joints. This significantly reduces the torque, the twisting force that the actuators need to provide, making the robot more energy efficient, potentially faster, and able to carry heavier loads with less powerful motors. This clever mechanism has even been used in direct drive robots that don't need traditional gear reducers, which further increases their precision and speed by eliminating backlash or slop in the gears.
Okay, that's a fantastic breakdown of serial linkages where links are connected one after another. But what about parallel linkages? How do those differ in their structure, and what sort of advantages might they offer?
Parallel linkages. They're fascinating because, as the name implies, the primitive joints can be formed in parallel as well as in series. This offers fundamentally different advantages, often in terms of stiffness, speed, and load capacity. A classic example is a 5-bar linkage. As the name suggests, it involves 5 links connected by 5 joints, including the base link. You can sort of visualize it as 2 simpler serial linkage arms joined together at a specific point, maybe forming a triangle with a base. The key characteristic here is a closed kinematic chain. Unlike an open serial chain where each joint's movement is independent of the next link down the chain, in a closed chain, the movement of one joint directly influences others in a constrained way. Imagine connecting 2 arms to a single object. They have to move together in a very specific coordinated dance. What's interesting mathematically is that the end effector's position is determined if just 2 of the 5 joint angles are known. For example, if the angles of joints 1 and 3 are set, all the other link positions and the end effector position are automatically determined by the geometry. If more than 2 joints were actively driven by motors, conflicts would arise because of that closed-loop chain constraint. So, typically, only 2 joints need to be active, operated by independent actuators, with the others being passive or free to rotate, allowing the system to achieve its constrained motion. Now, this type of parallel linkage offers some notable advantages. First, you can often situate both actuators at the base link. This makes the moving part of the robot arm much lighter compared to serial arms, where heavy motors might be fixed further out on the links. This lower inertia allows for much faster acceleration and deceleration. Second, a larger end effector load can usually be borne because the 2 sequential linkage arms share the load, distributing the weight more effectively and increasing overall stiffness. Another really significant parallel link robot structure is the Stewart structure, or Stewart platform. You often see these used in high-end flight simulators or motion platforms. This mechanism consists of a moving platform, a stable base, and 6 powered cylinders, or legs, connecting the platform to the base. The position and direction of full pose of the moving platform are determined by controlling the lengths of these 6 independent actuators. Since the load on the moving platform is distributed across all 6 arms or legs, this type of robot typically has a very large load capacity relative to its size and an incredibly fast dynamic response. They're exceptionally stiff and precise, making them ideal for highly dynamic, high-force applications where precision under load is critical.
That's truly a deep dive into the physical forms, really revealing how structure dictates function. But a robot's body, no matter how brilliantly engineered, it's nothing without a brain, right? How do we actually make these complex mechanical systems move and respond exactly as intended?
Making robots smart control loops of robotic systems.
Exactly. You've got the body, and now you need the control. We want robots to perform tasks that otherwise intelligent physical beings might do. Just like biological nervous systems are often thought of as these incredibly complex control networks for living organisms, controlling a robot effectively requires a series of critical steps that form a continuous feedback loop. We need to, first, be able to explain or represent the robot's position and overall state. Then we need to continuously sense the robot's current state using various inputs from its environment, from its own internal mechanisms. Next, critically, we have to compare its current state to a desired state or a target that we've given it. Is it where it should be? Based on that comparison, that difference or error, we select and issue the necessary commands to its motors and actuators to achieve that desired state. Then we translate those commands into precise physical actions moving a joint applying force. And finally, crucially, we continuously estimate the effect of those physical actions, feeding that information back to inform the next decision, the next comparison. This creates this relentless cycle of awareness, action, and adjustment.
Okay, so understanding the robot state is absolutely fundamental to this whole process. What does that comprehensive picture encompass? Is it just its physical location, or is there more to it?
Oh, it's definitely more than just location. The robot state is indeed a comprehensive picture, including several layers of information that are vital for intelligent control. You have the physical states. These are the most tangible aspects, like its precise position in 3D space, its orientation, often called its pose, its velocity, how fast it's moving, and its acceleration, how quickly its speed or direction is changing. Then there are the sensor states. This is what the robot's sensors are currently perceiving from the environment. Is it seeing an obstacle with its camera? Feeling pressure with its gripper, getting distance readings from its LiDAR. You also have actuator states. What's the current status of its motors and other movement components? Are they on, off, running at a certain speed, exerting a specific amount of force? And importantly, there are internal states. This is where the brain or the planning part truly comes in. This covers things like its current plans, its assigned tasks, its sub-goals, and its active behaviors. This is the more abstract layer of its mind, you could say.
Right. And this intricate dance of sensing, comparing, and acting brings us directly to the core of control engineering, doesn't it? That whole discipline.
Exactly. Control engineering is the critical application of mathematical techniques specifically to design algorithms and devices to control processes or machinery. And it always necessitates a precise model of the entity that is being controlled, whether that's a single robot joint, an autonomous car, or an entire chemical plant. What's truly powerful, and this is key, is that if a system can be modeled accurately by a set of linear differential equations, basically, equations that describe how things change over time in a predictable way, then there are well-understood mathematical techniques for finding exact analytical solutions. This allows engineers to design controllers so that the outcome of the system, its behavior, is precisely the requisite one. It gives you incredible predictability and accuracy, even in very complex systems. This mathematical rigor is really what allows for such precise and reliable control.
So for any system that needs controlling, what are the basic components that make up a control system? The fundamental building blocks that allow it to function and self-regulate.
Yeah, a typical control system includes 4 fundamental components that have to work together in harmony to achieve that desired outcome. First, you need a target value. This is the appropriate or desired operating point of the overall system. What do you want it to be doing? Think of setting a specific temperature on your thermostat. That's your target value. Second, you need the measured value. This is the actual operating point of the system at any given moment. It's often affected by external factors, like a door opening and letting cold air in, or internal factors like how much heat the furnace is actually producing. This is what the system is really doing right now. Third, there's the difference value, which we often just call the error. This is the critical discrepancy between the target value and the measured value. This difference is what gets translated into feedback for the system. If the room is 18 degrees, but you want 20, the error is plus 2 degrees. And fourth, you have the control input. This is the primary adjustable point of the control system, the lever it can pull to influence the measured value. In our thermostat example, it's basically turning the furnace on or off, or maybe adjusting the gas flow. And encompassing all this, driving the process, is the control algorithm. This is the brain of the controller that determines how best to regulate that control input. It constantly monitors the difference value, the error, and adjusts the control input accordingly to make that difference as close to zero as possible, thereby keeping the system stable and on target.
And feedback is absolutely crucial here, isn't it? We hear about positive and negative feedback all the time, but what do they truly mean in this specific context of control systems?
Feedback is utterly crucial, yes. It's a continuous monitoring of sensors and reacting to their changes to guide the system's behavior. Without feedback, you're just operating blind. Positive feedback generally acts to amplify the system's state or output. The more there is, the more is added. This often leads to system instability or runaway effects. Think of audio feedback squeal, or a stampede where fear just amplifies more fear, or maybe a stock market bubble where rising prices encourage more buying, leading to exponential growth that eventually, usually, collapses. It's generally destructive or undesirable in control systems where stability is key. Negative feedback, on the other hand, acts to balance or stabilize the system's state or output. If a value gets too high, the system acts to turn it down. If it gets too low, it acts to turn it up. This is what keeps systems in equilibrium and is really the bedrock of stable control. Think of a thermostat regulating room temperature, a toilet mechanism refilling the tank after a flush and then stopping, or even our own bodies maintaining internal balance like blood sugar levels. Robots almost exclusively rely on negative feedback for stability and precise controlled operation. It's what makes them predictable and reliable in the face of disturbances.
Okay, so negative feedback is the key for stable robot control, ensuring that precision we need. What are the different types of controllers that actually utilize these principles to achieve that stability? Are there different flavors?
Yes, there are several types, ranging from the very simple to the highly sophisticated, each with its own characteristics and best applications. The simplest is the open-loop controller, OLC. Here, the controller sends an input signal to the plant, that's the system being controlled, like a motor, but it does not compensate for any disturbances that happen after that control signal is sent. The real effects are just assumed, not actually measured. So there's no feedback loop to match the actual outcome to the intended outcome. For instance, if you program a robot arm to move a certain distance based purely on how many times the motor should rotate, an unexpected obstacle or extra friction wouldn't be registered. The arm would just keep trying to execute the original command, potentially crashing or failing. OLCs are often used for very simple, maybe behavior-based systems where a specific trigger condition activates a behavior that just runs until the condition stops. They might be used if you simply can't measure your operating point directly or if the system's environment is highly predictable and never changes. But their effectiveness is very context dependent. For example, the same force applied by a robot might have very different effects depending on the surface it's pushing against, something an OLC wouldn't know. In stark contrast, the closed-loop controller introduces that vital feedback mechanism. Here, the actual results of the controller's actions are sensed and then compared with a reference, or the desired state. The resulting error signal, the difference, is then fed back to the controller, creating that continuous loop. This negative feedback is precisely what keeps the system's operations smooth, stable, and, importantly, responsive to changes or disturbances. Its key components are always the reference, what you want, the controller, which issues commands based on error, and the plant, the actuator carrying out those commands, all working together in that loop to minimize the error. Then there's the bang-bang controller, BBC. This is the simplest type of closed-loop controller. It usually operates with just two distinct states, maybe fully on or fully off, full power forward or full power reverse. Its job is simply to keep a monitored quantity at a specific target value. Then there's the bang-bang controller, BBC. This is the simplest type of closed-loop controller. It usually operates with just two distinct states. If the quantity is too high or too low relative to the target, the BBC compensates by switching to the opposite state to change it. This often leads to abrupt, continuous transitions between its two states. Think of an old-fashioned room thermostat that just clicks the furnace fully on when it's too cold and fully off when it's too hot. It works, but the temperature tends to swing or oscillate around the target. It's simple and effective for many basic systems, but it lacks finesse and precision. Finally, we get to the workhorse, the proportional integral derivative PID controller. This is ubiquitous in industrial control systems because it offers a remarkable balance of precision, stability, and responsiveness. Finally, we get to the workhorse. You see, closed-loop controllers that use only proportional control, reacting just to the current error, can become unstable if the gain, how strongly it reacts, is too high, or very sluggish if the gain is too low. And they often leave a small, persistent error called steady-state error that they can't quite eliminate. PID controllers solve this by employing the calculated error to evaluate an input to the plant based on 3 distinct control components, all working together. Proportional P control. This component's output is based directly on the actual error at the current moment. A larger error leads to a bigger immediate correction. It's like pressing the gas pedal harder if you're far below your target speed. It controls the initial response time to the error. However, high P gains, or large initial errors, tend to cause the system to overshoot the target and then oscillate around the desired value. And as mentioned, it often can't eliminate that last little bit of steady-state error on its own. Integral I control. This component is designed specifically to reduce or eliminate that steady-state error. It does this by integrating the actual errors over time. It's like remembering past errors. If there's a small, persistent error that the P control isn't fixing, the integral term will gradually build up over time and apply an increasing correction until the error is gone. Once the accumulated error reaches a certain threshold, the controller compensates more strongly. Now, you have to tune the integration time carefully. Too short an integration time can lead to undershoot or instability, while too long can result in significant overshoot. Derivative D control. This component looks at the rate of change of the error, essentially, how fast the error is increasing or decreasing. It's computed based on the difference between the current error and the previous error. Its output is proportional to this rate of change. It's like predicting the future error based on the current trend and applying the brakes preemptively if the error is decreasing rapidly towards zero. Its main job is to prevent oscillations caused by overshoot from the P and I terms. It decreases settling time by providing better dynamic response, effectively dampening swings, and allowing the system to settle quickly and smoothly near the target value. It generally has a very positive stabilizing effect. PID controllers have these 3 tunable factors or gains: Ki, proportional gain; Ki, integral gain; and Kd, differential or derivative gain. Critically, these parts are cross-coupled. Tuning isn't as simple as adjusting each one separately. Changing one affects how the others behave. It's a holistic tuning process, often done empirically through trial and error on the actual system. Few complex control systems can be engineered effectively without using all 3 PID components in some combination. While P components are almost always required, pure P controllers can be unstable. PI control, proportional plus integral, is often used when high accuracy isn't paramount, but quick convergence and eliminating steady-state error are important. PD control, proportional plus derivative, converges relatively quickly and significantly decreases oscillations as it approaches the goal, offering good stability. A full PID controller aims for the best of all worlds, accurately maintaining a position or state while balancing speed, stability, and minimizing overshoot. It might not always be the absolute fastest, but it's often the most reliable and precise for demanding applications.
Wow, okay. This is where the true engineering precision and, honestly, the elegance comes in, creating systems that are so responsive and stable. But how are these sophisticated mathematical commands actually translated into truly powerful physical movement, especially when we need a robot to exert some serious force, lift heavy things? Let's explore hydraulic systems.
The power behind the motion hydraulic systems.
Right. When we need a robot, or any machine really, to exert serious force, especially for heavier tasks, hydraulics often comes up as the go-to solution. But what exactly is hydraulics? Well, hydraulics is fundamentally the science of transferring force and/or motion using a confined liquid as the transmission medium. In a hydraulic device, power is transferred by pushing on this confined liquid. The energy transfer takes place because a quantity of that liquid is subjected to pressure. So to really operate these systems effectively, you need a basic understanding of the nature of liquids, particularly the most crucial property for this application. They are essentially incompressible. Unlike air, you can't really squash a liquid significantly.
Okay, so it's all about pushing on liquid that can't really be compressed. What's the core scientific principle, then, that allows hydraulics to generate such massive force, often from a relatively small input?
The core concept, and really the genius behind hydraulics, is Pascal's law. You might remember from physics class. This law states that pressure applied to a confined fluid is transmitted undiminished and equally in every direction throughout the fluid. This is absolutely crucial. Imagine you have a small piston pushing on a fluid with a certain force over a small area. That creates a pressure, force divided by area. Pascal's law says that pressure is transmitted equally throughout the entire confined fluid. Now, if that same fluid then pushes on a much larger piston, because the pressure is the same but acting over a much larger area, it will generate a proportionally huge output force, pressure multiplied by the larger area. It acts like a powerful mechanical leverage system, but using fluid instead of levers. Think of a small hand pump on a hydraulic jack easily lifting a heavy car. That's Pascal's law in action, multiplying force incredibly effectively.
That's truly fascinating, like a force multiplier built right into the system's design. So what are the key components of a typical hydraulic system then? What makes this fluid magic actually happen?
Yeah, a complete hydraulic system includes several essential parts working together in concert for proper functioning, control, and safety. Typically, it consists of a movable piston connected to an output shaft housed within an enclosed cylinder. This is where the pressurized hydraulic fluid acts to apply force or generate linear or rotary motion. A storage tank or reservoir for the liquid. This liquid is typically a specialized, high-density, incompressible oil chosen for its lubrication properties and stability. This reservoir holds the system's fluid supply. A filter is critical. It removes dust, dirt, metal particles, and other unwanted contaminants from the fluid. Even tiny impurities can cause significant damage to the precision components like pumps and valves over time, so clean fluid is essential. An electric pump, or sometimes engine-driven, that draws fluid from the tank and pumps it into the system under pressure. The pump's capacity depends on the system design requirements, flow rate, and pressure needed. These pumps usually deliver a relatively constant volume per revolution, building up the pressure needed to do work. A pressure regulator or a relief valve. This is a vital safety component. It prevents indefinite pressure buildup if the system output is blocked or reaches its limit, which could otherwise cause hoses to burst or components to fail catastrophically. It does this by redirecting excess fluid flow back to the storage tank when a preset pressure limit is reached. A control valve, or valves. This is how you direct the power. It supervises the fluid flow, directing the pressurized liquid to specific ports on the cylinder or hydraulic motor to control the movement. For example, fluid might be directed to port B to extend a piston, or to port A to retract it. The valve can also block flow to ports, effectively holding the actuator firmly in position. This is how the system's commands are translated into controlled physical motion. And crucially, there's leak-proof closed-loop piping, or hoses. These connect all the components, ensuring the fluid stays contained and under pressure. Leak prevention is essential for both environmental safety — hydraulic fluid can be nasty — and economic reasons, as lost fluid means lost power and potential contamination. Additionally, you might find other accessories like electric motor starters, flow control valves to regulate speed, travel limit switches, pressure gauges, and overload protection devices, all integrated to ensure precise, efficient, and safe operation.
Okay, that's a lot of intricate parts and specialized fluid working in unison. Given their immense power and precision, where are hydraulic systems most commonly applied in the world around us? They seem pretty specialized.
Well, they are specialized for high force, but they're surprisingly widespread. Hydraulic systems are mostly used for precise control of larger forces, where you need high power density and consistent force application. Their main applications generally fall into 5 broad categories, showing just how pervasive they are. Industrial applications — this is a huge area. Think of plastic processing equipment. Injection molding machines use massive clamping forces. Steel making and prime metal extraction machinery. Automated production lines needing heavy lifting or pressing. Textile machinery. The machine tool industry, like giant metal forming presses. Paper industries, powerful loaders and crushers. Heavy-duty robotic systems, especially those handling very large payloads. And R&D equipment that requires applying or measuring immense forces. Mobile hydraulics. This category covers pretty much all heavy-duty equipment that moves. Think massive tunnel boring machines, agricultural tractors and combines, earth-moving machinery like excavators, backhoes, and bulldozers, material handling equipment like forklifts and cranes, commercial vehicles like dump trucks and garbage trucks, large-scale irrigation systems, rail equipment, building and drilling rigs for construction and mining, and other demanding construction machinery. Hydraulics provide the muscle. Automobiles. Even in our cars, hydraulics are crucial. They're used in powerful brake systems using brake fluid, shock absorbers for a smoother ride, power steering systems for easier control, and sometimes even in things like convertible top mechanisms or windshield lift systems. Marine applications. This covers everything from large ocean-going vessels and fishing boats to complex naval equipment. Hydraulics are used for steering systems, operating large cargo hatches, anchor winches, stabilizers, and deck cranes in the harsh marine environment where robustness and power are critical. And finally, aerospace equipment. Here, reliability and power-to-weight ratio are key. Hydraulic apparatus and systems are used for critical flight control surfaces, like moving the ailerons, elevators, and rudders, extending and retracting landing gear, aircraft braking systems, and sometimes even actuation systems in spaceships, rockets, and airplanes. They were vital for precise and powerful actuation under extreme conditions.
Wow, okay, they're absolutely everywhere then, providing the brute strength and the precision control behind so much of our modern world. So what are the big advantages, and conversely, what are the significant disadvantages of using hydraulic systems, say in robotics or other demanding applications?
Right, it's crucial to weigh the pros and cons when deciding if hydraulics are the right choice for a specific design. First, the advantages. The using compressible fluid, as we said. This leads to very high efficiency and power transmission because almost no energy is lost to compressing the fluid itself, unlike pneumatic systems using air. They deliver incredibly consistent power results. Force and speed can be maintained very steadily, which is often crucial and generally superior compared to pneumatic or purely mechanical drive systems, especially when dealing with varying loads. The probability of leakage in a well-designed and maintained system is generally less than in pneumatic systems. Air is just harder to seal completely than oil. Maintenance costs can actually tend to be lower for hydraulic systems over their lifespan, assuming proper design and care, partly due to their inherent robustness and often fewer high-speed moving mechanical parts susceptible to wear compared to complex gear trains. And they perform exceptionally well in hot environmental conditions. The fluid itself can help dissipate heat, and the components are generally less sensitive to high temperatures than, say, complex electronics or electric motors might be. However, there are also notable disadvantages to consider. The components themselves, the storage tank, piping, cylinder, piston, can be susceptible to corrosion from the hydraulic fluid over time, especially if the wrong fluid is used or if water gets into the system. So careful material selection for components and choosing the appropriate hydraulic fluid are essential for longevity. The overall architectural weight and size of the system can be substantial. You need relatively bulky components like large pumps, reservoirs, accumulators, and thick, strong piping or hoses to handle the high pressures. This makes hydraulic systems generally unsuitable for smaller, more delicate instruments or lightweight mobile robots, where space and weight are critical constraints. System cleanliness is paramount. Even tiny impurities or contaminants in the hydraulic fluid can permanently harm the complete system by scratching precision surfaces, clogging narrow passages and valves, or damaging seals. This necessitates careful filtration and strict cleanliness protocols during assembly, operation, and maintenance. Leakage of hydraulic fluid, while perhaps less probable than air leaks, is a much more critical issue if it does happen. This is due to the potential environmental hazards. Hydraulic fluids can contaminate soil and water and create slip hazards. So, proper prevention methods, robust seals, and containment strategies are absolutely vital. And finally, the hydraulic fluids themselves, if not disposed of properly at the end of their life or after a leak, can be harmful to the environment. They pose an ecological concern that requires responsible management and disposal procedures.
Okay, so incredibly powerful and precise, yes, but definitely with some significant considerations regarding size, the need for absolute purity, and that environmental impact. Now let's switch gears pretty dramatically. We've talked about the body, the power. Let's talk about how robots actually understand their own position and movement in space. This is where robot kinematics comes into play, right?
Robots' sense of self-kinematic analysis.
Precisely. This is where robot kinematics steps in. You can think of it as the robot's fundamental sense of self, its geometric awareness in space. Robot kinematics is all about describing the position and the orientation of the robot's end of arm, or maybe the end effector attached to it, purely as a function of its joint positions in time. Crucially, classical kinematics does this without considering the effects of forces, mass, or inertia. We're not worried about why it moved, just where it is. Our sole focus here is the mathematical representation of this position and orientation in a way that the robot's control system can understand and use.
Right. And I understand there are two main sort of opposite problems within kinematic analysis that engineers constantly need to solve to make robots useful.
Yes, exactly. There are two fundamental and, in a sense, inverse types of problems in kinematic analysis that we need to solve to make a robot move intelligently and purposefully. One. The first is forward or direct kinematics. This is about figuring out the position and orientation coordinates of the end effector given a specific set of joint coordinates. So you know precisely where each joint is positioned or angled, the joint space variables, and you want to calculate exactly where the hand or tool ends up in 3D Cartesian space, your task space variables. It's like knowing all your arm joint angles and being able to instantly calculate precisely where your fingertip is pointing. Two. The second is backward, or inverse kinematics. This is often the more challenging and certainly more computationally intensive problem. It involves determining the specific joint coordinates, the angles or displacements for each joint that are required to achieve a desired location and orientation of the end effector in Cartesian space. This is very often what we actually want the robot to do. Go to this specific point in space with this specific orientation, and then the robot's brain has to figure out exactly how to contort its arm, which joints to move by how much to get there. It's like wanting your fingertip to touch a specific spot on a table, and then your brain instantaneously calculating exactly how to bend your shoulder, elbow, and wrist joints to make that happen.
Okay, let's focus on direct kinematics first then. What exactly is that process, and why can it be relatively straightforward for some common robot types, but incredibly complex for others?
Right. So in robotics, we primarily use those two types of coordinates we just mentioned to describe the system's configuration. First, there's Cartesian space, often called end effector space or task space. This uses the familiar x, y, z coordinates plus orientation angles to describe the position and orientation of the end effector, focusing on the task it needs to perform. The other type is joint space. This defines the precise configuration of the mechanical linkage itself through its specific joint angles for revolute joints or linear displacements for prismatic joints. This describes the robot's internal state. Direct kinematics is essentially the map, or the mathematical method, used to get from the joint space coordinates to the end effector coordinates in Cartesian space. Now, for simple open chains, like a basic 3-arm manipulator, meaning 3 revolute joints connected in series, like a simplified arm, the process is relatively straightforward. You basically just substitute the known joint angles into a set of derived geometric equations, and out pops the Cartesian XY position and the orientation of the end effector. In fact, for almost all purely serial chains, direct kinematics is generally, direct and analytically solvable. It usually gives you a single, unique answer for the end effector pose given the joint angles. However, it becomes much more complex and can often yield multiple possible solutions, or sometimes even no physically reachable solutions at all, if the robot structure contains one or more closed loops. Like those parallel linkages we discussed earlier, the 5-bar linkage or the Stewart platform. In such cases, the geometric interdependencies created by the closed chain mean that a given set of input joint positions, the ones you control, might correspond to several different possible end effector positions and orientations. Or, depending on the geometry, there might be no way for the structure to physically reach that configuration at all. For example, it's known that even a relatively simple planar parallel manipulator might have anywhere from 0 up to 6 distinct valid solutions for its end effector position based on its specific link lengths and input joint angles. This complexity is why closed loop or parallel systems require much more sophisticated analysis, and why direct kinematics isn't always quite so direct for them.
Right, okay. So it's about translating those abstract joint movements into concrete real-world positions. Is there a standard, almost universal algorithm or approach that engineers use to tackle this direct kinematics problem, especially for the more common serial robots, like a recipe?
Yes, absolutely. There's a widely adopted, general algorithmic approach for direct kinematics that provides a systematic way to solve this problem, particularly for serial manipulators. It's often taught to engineering students as the standard way to understand the step-by-step process of describing a robot's geometry mathematically. First, you start by meticulously drawing a detailed sketch of the robot's physical structure, really visualizing its links and joints. 2, then you systematically number the links, typically assigning the fixed base as link 0 and the very last link, the one holding the end effector, as link n, where n is the number of joints. 3. Next, you identify and number each robot joint sequentially, usually from 1 up to n, starting from the joint closest to the base. 4. For each joint I, you then draw an axis z, carefully aligning it with the axis of motion for that joint. If it's a revolute joint, z is the axis of rotation. If it's prismatic, z is the direction of sliding. 5. After establishing the z-axis, you determine the common normal length a1 between axis z1 and axis z. This distance is measured along a line that is mutually perpendicular to both z1 and z, and this perpendicular line defines the direction of the xi1 axis. 6. You then explicitly draw this axis xi1. The next crucial step is to determine the link twist IA. This is the angle between the axis Z1 and the axis Z, measured around the xi1 axis. This describes how much one link is twisted relative to the previous one geometrically. 8. Then you determine the joint offset die. This is the distance measured along the Z-axis from where xi1 intersects Z to where the xi-axis intersects Z. It represents any linear offset along the joint axis. 9. Following that, you determine the joint angle. This is the angle measured around the z-axis, from the she1 axis to the she axis. For a revolute joint, this c is the variable joint angle itself. For a prismatic joint, I is usually fixed and di becomes the variable joint displacement. 10. Finally, using these four parameters, A, 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 D, for each linked joint pair, you write the mathematical transformation matrix, a 4x4 matrix representing rotation and translation, that describes the coordinate frame of joint A relative to joint I1. Then you concatenate these individual transformation matrices, essentially. Multiply them together in the correct order from base to end effector to get the single overall transformation matrix. This final matrix precisely describes the end effector's position and orientation relative to the robot's space ring, given all the joint variables.
Wow, that sounds incredibly precise, almost like creating a standardized mathematical blueprint for any robot's anatomy. And that leads us directly, I believe, to a widely used convention called the Denovet-Hartenberg, or DH method. What exactly is that, and why has it become so significant in the world of robotics?
Yes, the Denovet-Hartenberg, or DH representation. It has become almost universally adopted in robotics research and industry, especially for deriving the kinematic details of serial robotic manipulators. Its profound significance really lies in its highly systematic and algorithmic approach. Before DH came along, figuring out the kinematics for each new robot arm design was often a bespoke, complex, and error-prone mathematical exercise. DH provided engineers with a universal language or framework to describe the geometry of any serial robot arm in a consistent way. The procedure begins with systematically assigning and labeling an orthonormal, mutually perpendicular XYZ axis coordinate system to every robot joint, following a strict set of rules. This methodical approach allows us to mathematically describe one joint's frame of reference relative to the next adjacent joint's frame, and ultimately, by chaining these descriptions together, to assemble a complete and unambiguous geometric representation of a robot's entire structure. This consistency is absolutely crucial for both designing robots and programming their movements accurately. The DH method uses those four specific parameters we just discussed to uniquely describe the geometric relationship between consecutive joint axes for each link dot AI, or sometimes AI1, depending on convention. This is the link length, the distance measured along the aphic axis, the common normal, from the intersection with the z-axis to the origin of the next frame, frame I plus 1, high I. This is the link twist, the angle measured about the c-axis from the z-axis to the z plus 1 axis. It describes how much the link twists geometrically from one joint axis to the next at ci. This is the link offset, the distance measured along the z-axis from the origin of the previous frame, frame I1, to the intersection of the ei axis with the xi-axis. For a prismatic joint, this die is the variable joint displacement. This is the joint angle, the angle measured about the z-axis from the xi1 axis to the i-axis. For a revolute joint, this die is the variable joint angle. In the DH convention, the general transformation between two adjacent coordinate frames, say frame I1 and frame I, is elegantly described as the product of four basic ordered transformations defined by these four parameters. A translation along the previous z-axis by LAI, a rotation about the previous z-axis by RAI, a translation along the new x-axis by AI, and finally a rotation about the new x-axis by AI. This standardized sequence, along with specific rigorous rules, often labeled D1 through D8 in textbooks, for establishing the coordinate systems, aligning the axes, locating the origins, and defining these link and joint parameters, enables engineers to systematically create a complete kinematic model. This allows for accurate simulation, analysis, and control programming for virtually any serial manipulator structure. It essentially provided the common mathematical blueprint that allowed for the rapid development and widespread adoption of complex robotic systems.
So it's truly a standardized language, a universal grammar for describing a robot's geometry and potential motion. That sounds absolutely essential for building complex systems and ensuring different robots or software tools can understand each other. Speaking of complex mathematical approaches that underpin robot movement, what are quaternions, and why are they so important in the world of robotics, especially when they sound like something straight out of a sci-fi novel?
Thinking in 4D principles of quaternion.
Quaternion definitely does sound a bit sci-fi, but they are indeed fascinating mathematical objects with very practical applications. Quaternions are fundamentally numbers. They're similar to real numbers or complex numbers in that they can be added, subtracted, multiplied, and divided, following specific algebraic rules. What's unique about them is that they're composed of four numbers that work together as a single entity. They were discovered back in the 1800s, most famously by the brilliant Irish mathematician William Rowan Hamilton in 1843. Legend has it, he was walking along a canal in Dublin, had a flash of insight about their multiplication rules, and actually carved the fundamental formula into the stone of Brougham Bridge. They are essentially an extension of complex numbers, which have one real and one imaginary part. Quaternions add two more imaginary components, giving them 4 parts in total. Some early enthusiasts even believed quaternions could express everything in our universe, the 3 dimensions of space plus 1 dimension for time, due to this inherent 4-component structure. They represent a deep and beautiful connection within the foundations of algebra and number theory.
4 components, that's definitely unique. How do they mathematically break down? How does that 4-part structure relate to their practical use in robotics?
Right, so of the 4 components, one is a real scalar number, which we often denote as S, or sometimes Q0W. The other 3 components form a vector V in an imaginary Eich space, typically represented as Q1Q plus Q2J plus Q3K, or I plus IJ plus EK. So a quaternion Q can be concisely written as QSV, or perhaps QW plus E plus IJ plus EK. This unique structure allows them to elegantly encode both a rotation axis, represented by the vector part V, and an angle of rotation, related to both S and the magnitude of V, within a single mathematical entity. This makes them incredibly efficient and compact for representing orientations or rotations in 3D space.
Okay, efficient and compact. So how are they actually used in the real world, especially in robotics and other high-tech fields? What specific problem do they solve for engineers and programmers?
In practice, their most crucial and widespread application for us, in fields like robotics and graphics, is as an incredibly elegant and computationally efficient means of representing and manipulating orientations and rotations of objects in 3-dimensional space. They are extensively used in a surprisingly wide array of fields precisely because of their powerful mathematical properties. Hugely important in computer graphics for calculating smooth and efficient object rotations, avoiding visual artifacts like jerky movements that can happen with other methods. Fundamental in control theory, especially for the precise management of dynamic systems where orientation matters, like controlling the attitude of flying vehicles or stabilizing camera platforms. Used in signal processing, particularly where rotational data or transformations are critical. Absolutely crucial in attitude controls for things like spacecraft, satellites, drones, missiles, or even the motion sensors in your smartphone. Maintaining and accurately controlling orientation is paramount in these applications. They appear in physics, particularly in mechanics and quantum mechanics for describing rotations and spin, and in orbital mechanics for describing the orientation and rotational motion of celestial bodies or satellites. They're even finding applications in emerging fields like quantum computing and the design of quantum circuits, highlighting their fundamental mathematical significance in representing certain quantum states and operations.
So they're pretty much essential for anything involving precise 3D orientation and rotation. What are their distinct advantages over other methods, say using Euler angles like roll, pitch, yaw, or maybe 3x3 rotation matrices, which might seem simpler or more intuitive at first glance?
That's the key question, really. While Euler angles might seem intuitive, and matrices are explicit, quaternions offer several significant advantages that make them the superior choice for representing rotations in many complex real-time applications, especially robotics. Critically, they powerfully avoid gimbal lock. This is a notorious problem that can plague systems using sequential rotations like Euler angles. In certain orientations, 2 rotational axes can align, causing the system to effectively lose a degree of rotational freedom. Imagine an airplane pitching straight up its yaw and roll controls might suddenly become entangled or ineffective. It's like a mathematical blind spot. Quaternions, because they represent rotation as a single operation, elegantly sidestep this problem entirely, ensuring full, unambiguous 3D rotational control at all times. This is vital for robots moving freely in space. They generally have faster multiplication algorithms for combining successive rotations compared to multiplying 3x3 rotation matrices. Matrix multiplication involves many more floating point operations. Quaternion multiplication is computationally cheaper, which is a significant advantage in real-time control systems like robots or simulations, where every millisecond counts for smooth, responsive movement. They are simpler and more numerically stable to normalize than rotation matrices. Over many calculations, small numerical errors can accumulate, causing a rotation matrix to drift away from being a valid rotation. For example, its columns might stop being perfectly orthogonal. Renormalizing a matrix is computationally expensive. Renormalizing a quaternion, making its magnitude 1 again, is a much simpler and faster operation, helping to maintain accuracy over long sequences of operations. They are particularly excellent for interpolation between different orientations. Finding the shortest and smoothest rotational path between 2 orientations, known as SLIRP, spherical linear interpolation, is mathematically straightforward and elegant with quaternions. This is vital for smooth animation, but also for generating fluid and energy-efficient paths for robot arms or mobile robots. And related to normalization, they are mathematically stable and compact, using only 4 numbers compared to 9 for a rotation matrix. This compactness saves memory and bandwidth. And their stability makes them well suited for things like statistical analysis of rotations, which can be prone to ambiguities or errors with other methods. They offer greater robustness for complex control algorithms.
And you often hear about unit quaternions. What are those specifically, and why are they particularly useful in this context?
Right. For convenience, mathematical elegance, and computational efficiency, especially in robotics, computer graphics, and attitude control, we almost exclusively work with unit-length quaternions, often just called unit quaternions. These are simply quaternions where their length or magnitude, calculated similarly to the length of a 4D vector, is exactly equal to 1. Mathematically, all possible unit quaternions correspond to points on the surface of a 4-dimensional hypersphere of radius 1. Now, a 4D surface is obviously hard to visualize directly, but you can think of it conceptually as an extension of the familiar concept of a 2D spherical surface, like the Earth, existing in 3D space. A sphere represents all possible 3D directions from a central point. Similarly, the 4D hypersphere of unit quaternions represents all possible 3D orientations or rotations. A unit quaternion can perfectly and uniquely represent a rotation by a specific angle around a specific unit axis in 3D space using a simple formula involving cosine and sine of half the angle. If the rotation axis A is itself a unit vector, then the resulting quaternion Q representing that rotation will also automatically have a length of 1. This unit length property is what makes them so powerful, compact, unambiguous, and elegant for describing spatial orientations without redundancy or gimbal lock issues. It simplifies calculations and ensures a consistent normalized representation of rotation.
Wow, okay. That's truly diving deep into the fundamental math behind the motion. It's amazing how these abstract concepts enable such concrete physical capabilities. Now, once we have the physical structure defined and the mathematical understanding of how robots move, how do we actually tell a robot what to do? How do we program it to perform a specific desired task in the real world?
Teaching the robot programming of robots.
Right, exactly. We know how they're built. We know the math behind their movement. But then comes the practical step. How do you actually instruct a robot? Okay, I need you to do this specific task precisely like this. What are the different programming methods that have evolved over time to give these machines their instructions for a given work cycle? There are primarily 4 broad categories of methods, ranging from the very simple and hands-on to the highly sophisticated and computer-based, really reflecting the increasing complexity of robots and the tasks we ask them to do. 1, there's the manual method. 2, the walkthrough method. 3, the lead-through method. 4, and finally, the more modern approach, offline programming.
Okay, let's start with the manual method. That sounds incredibly hands-on, almost rudimentary.
It is, absolutely. The manual method isn't really programming in the way we usually think of it in computer science today. It's much more akin to physically setting up or configuring a simpler machine. It involves physically adjusting things like mechanical stops, setting cams or limit switches, or maybe manually inputting settings directly into the robot's dedicated, often simple control unit. There's typically no sequence of stored code being written or executed. This method is really only sufficient for simpler, often lower technology robots used for very short, highly repetitive work cycles, like basic pick-and-place actions where high precision isn't the main goal and the sequence never ever changes. Think of it more like adjusting physical dials or levers on an old machine rather than writing software.
Okay, what about walkthrough and lead-through? They sound quite similar. Both seem to imply some kind of physical interaction during the programming phase. What's the actual distinction between those two?
They do sound similar, and they are both considered online methods, meaning the robot is physically present and often taken out of production for the programming or teaching process. But there's a key distinction in how the programmer interacts with the robot. With the walkthrough method, the programmer literally grabs the robot's arm or end effector and manually shifts or guides it physically through the entire desired motion sequence of the work cycle. They physically move the robot where they want it to go. Each movement, each key position or point the robot's arm passes through, is then recorded into the robot's memory for later playback during actual production. Usually, the speed of the movements during playback can be controlled separately, so the programmer during walkthrough can focus purely on getting the sequence of positions and the path correct, without worrying about doing it at the final production speed. This method is particularly suitable for tasks like spray painting, where the continuous path and orientation of the spray gun are critical, or maybe for arc welding, where the welding torch needs to follow a specific seam precisely. It's very intuitive, almost like teaching by physical example, like guiding someone's hand. The lead-through method, on the other hand, makes use of a device called a teach pendant. This is typically a small handheld controller, often with buttons, switches, dials, and sometimes a joystick. Using this pendant, the programmer drives the robot electronically through its motion sequence, usually controlling one joint or one Cartesian axis at a time. Like the walkthrough method, each key, point, or motion segment is recorded into memory for future playback during the work cycle. The lead-through method is very, very popular, especially for industrial robots, due to its relative ease and convenience. It offers more precise and granular control over individual joint movements compared to physically manhandling the arm, especially for larger, heavier, or more powerful robots. You're still leading the robot through its task, but you're doing it remotely with a digital controller, like using a remote control car.
Okay, so these online methods, walk-through and lead-through, they sound quite intuitive and maybe practical for certain scenarios. But I imagine they come with some significant limitations, especially as robot tasks get more complex or need to integrate with other systems.
They certainly do. While they are intuitive and relatively easy to learn, these online or lead-through programming methods come with several inherent disadvantages that really highlight why more advanced methods were needed. First off, it's simply not practical or even safe for programming very large or very heavy robots. Physically moving them, walk-through, or precisely driving them point by point with a teach pendant, lead-through, can be extremely cumbersome, time-consuming, potentially dangerous, or even impossible for the largest machines. Achieving very high accuracy, especially for complex paths like perfectly straight lines between distant points or smooth circular arcs, is difficult. You're essentially teaching a series of discrete points in space, and the robot controller then interpolates the path between them. Getting that interpolation to be exactly the geometrically perfect path you want can be challenging with manual teaching. It's notoriously hard to edit out unwanted operator moves or accidental jitters that might have been recorded during the teaching process. If you make a mistake mid-sequence, you often have to reteach that entire segment or even the whole program, which is inefficient. Incorporating external sensor data, like input from a vision system identifying a part's location, or feedback from a force sensor during assembly into the program logic, is very difficult or impossible with these purely taught methods. This significantly limits the robot's ability to adapt to variations in its environment or parts. Synchronizing the robot's movements precisely with other machines or equipment in the work cell, like coordinating with a CNC machine or a conveyor belt, is challenging and often relies on simple timing or basic digital signals, which can be prone to errors and lead to potential bottlenecks or inefficiencies in a larger automated system. And finally, these point-based teaching methods often require a significant amount of memory space in the robot's controller just to store all the recorded points and associated movement data, which could be a practical limitation for very long or complex sequences.
That makes perfect sense. The limitations become clear when you think about complex integrated automation. So where does offline programming come into the picture? It sounds like it was developed specifically to address some of these issues and bring a new level of sophistication to how we instruct robots.
Yes, exactly. Offline programming represents a more advanced, powerful, and flexible approach that directly addresses many of the limitations inherent in the online teaching methods. As the name suggests, it involves creating the robot program away from the actual robot itself, typically using software running on a computer terminal or a dedicated workstation. It's very similar in concept to how NC, numerical control programs for machine tools, are often generated using CAM, computer-aided manufacturing software. You write and simulate the code in a separate virtual environment first. Once the program has been fully formulated, often simulated graphically to check for collisions and path accuracy, debugged and optimized, it's then downloaded or loaded directly into the robot's controller memory for execution during the actual work cycle on the factory floor. A major advantage of offline robot programming is that the robot's valuable production time is not lost while it's being taught a new task. The programming, simulation, and debugging can be completed entirely offline, perhaps while the robot is still busy working on its previous job, or even before the robot is physically installed. This leads to much higher utilization rates for the robot and its associated equipment, which translates directly into significant economic benefits in manufacturing. Another really significant advantage, especially in modern factories, is the potential for tightly integrating the robot programming environment into the factory's broader CAD/CAM computer-aided design manufacturing database and overall digital information system. This allows for a seamless flow of design data, like 3D models of parts and fixtures, directly into the robot programming and simulation process. This makes the programming faster, much more accurate, basing paths on the actual digital design, and enables complex simulations and virtual commissioning of entire work cells before any physical hardware is even set up.
And with this shift to computer control and offline programming, we absolutely need specialized programming languages, right? It's not like just teaching points anymore. You need actual code, logic, structure.
Exactly right. Those non-computer controlled robots, or the ones programmed purely by manual or lead-through methods, don't really necessitate traditional programming languages in the software sense. They rely on stored points and sequences. But with the widespread introduction of computer control for robots, the opportunity and indeed the necessity arose to develop computer-oriented robot programming languages. These languages offer much greater flexibility, sophisticated logic capabilities like conditional branching, loops, subroutines, integration with sensors, communication features, and overall power compared to simple point-to-point teaching. They allow you to write actual structured programs using constructs familiar from general computer programming. One historically significant example is the VAO language. This language was specifically developed by Unimation for their PUMA robot series. PUMA stood for Programmable Universal Machine for Assembly, which was very influential. VAL is essentially an offline capable language, meaning the program structure and logic could be written offline. However, interestingly, the specific point locations used within the work cycle were often still defined or touched up using the lead-through-teach pendant method. So it was often a kind of hybrid approach. VLL declarations and commands were typically branched into two main groups. Monitor commands. These were essentially administrative guidelines or commands that directed the overall operation of the robot system, like operating system commands. Functions included preparing the system for the user to write or edit programs, defining points in space, commanding program execution, listing programs on the screen, checking status, etc. Think of them as the interface for managing the robot and its programs. Examples included commands like edit to enter or modify program code, execute to run a stored program, speed to set the robot's overall movement speed, and here to record the robot's current position and assign it a name. Programming instructions. These were the actual statements used within a VLO program to define the robot's actions. Often one statement corresponded to one logical movement or action of the robot's arm, wrist, or gripper. Examples included instructions like move for point-to-point motion where the path between points isn't critical. Moves for controlled straight-line motion between points. Aprio, approach a defined point along the tool axis by a specified distance. Apres, approach in a straight line. Depart, move away from a point. Open A, open the gripper immediately. Close CI, close the gripper immediately. And exit to end the program execution. Another important and perhaps more ambitious early language was the MCL language. This stands for Machine Control Language, and it was originally developed by McDonnell Douglas. MCL was heavily based on the highly successful APT, automatically programmed tools, and NC numerical control languages, which were the standard for programming automated machine tools for decades. MCL was specifically designed with a broader scope to control entire manufacturing cells, not just individual robots. It aimed to be a universal language for integrated automation. MCL was essentially an enhancement of APT, possessing additional options and features specifically needed to do offline programming of complex robotic work cells involving multiple devices. Supplementary vocabulary words were created within MCL to provide extra capabilities deliberately intended to be covered by the language, which included commands for integrating vision systems, triggering inspection routines, and managing control signals between different machines in the cell. MCL also allowed users to define macros, which are like creating your own custom subroutines or high-level commands, making it convenient to reuse code for specialized or repetitive application tasks. An MCL program, like APT, typically needed to be compiled by a processor to produce a lower-level output file, often called a CLFIE or cutter location file, carrying over the NC terminology, which was then post-processed and loaded onto the specific robot or machine controller. Some important commands indicative of MCL scope included device, to select which machine or robot the subsequent commands apply to, send, to send data or signals to a device, receive, to receive data or status, work key T, to define the location of a workpiece, abort, to stop a process, task, to define or call a specific task or subroutine, region, to define a specific working area or boundary, and locate, perhaps using a sensor to find an object's position. This really illustrates the evolution from just controlling a single robot's motion to orchestrating entire automated environments with multiple interacting components.
Okay, It's crystal clear that robot programming has become incredibly sophisticated, moving far beyond just teaching points to encompass complex logic, sensor integration, and even coordinating whole work cells. But for a robot to truly interact effectively with and adapt to its environment, it can't just blindly follow pre-programmed instructions, no matter how complex. It really needs to perceive the world around it in real time. Let's talk about the robot's senses. How do they perceive their surroundings?
The robot sensors of robots.
You've hit on an absolutely crucial point there. For many of the more advanced robot applications we see today and envision for the future, simple workstation control using basic interlocks or just running fixed programs is simply not sufficient anymore. To perform tasks in a suitable, flexible, and safe way, especially in dynamic or unpredictable environments, robots must take on more capabilities that mimic human-like senses. These allow them to perceive and react to their surroundings. These senses and capabilities incorporate crucial functions like vision and the associated hand-eye coordination, the sense of touch, and even the rudimentary beginnings of hearing or voice recognition. Accordingly, we can broadly divide the types of sensors commonly used in robotics into three main groups. 1. First, and arguably most impactful recently, are vision sensors. 2. Second are tactile and proximity sensors, the sense of touch and near touch. 3. And third, voice sensors or speech recognition systems.
Okay, let's start with vision sensors. This sounds like literally giving robots eyes to see the world. How does that actually work, and what kinds of breakthroughs does it enable for robot capabilities?
Exactly. Vision sensors, or machine vision, is one of the most exciting and rapidly developing areas in robotics research. And computerized vision systems are fast becoming a truly fundamental technology in the automated factories of the future, and even in our homes. Robot vision is typically made possible by means of a video camera, often one or more high-resolution digital cameras combined with an adequate and usually carefully controlled light source. Lighting is critical for good vision. And of course, a powerful computer program to process the complex image data captured by the camera. The camera itself can be mounted either directly on the robot's arm or end effector, providing a close-up hand-eye view that moves with the robot. Or it can be mounted in a fixed, stable position overlooking the robot's workspace, giving it a broader overview. Specialized computer software, increasingly leveraging sophisticated AI algorithms like deep learning, enables the vision system not just to see an image, but to interpret it, to detect the presence of an object, determine its precise position and orientation in 3D space, identify what type of object it is, read barcodes or text, or even assess its quality. This gives the robot crucial, real-time information about its environment that it simply didn't have before.
That's incredible. It really opens up possibilities. So with these vision capabilities, what new, more advanced operations can a robot actually perform that would be impossible for a blind robot just following coordinates?
Vision capacity enables a whole new class of operations, making robots much more flexible and adaptable. For example, 1. Retrieving parts that are randomly oriented on a conveyor belt or jumbled in a bin. Instead of needing parts presented precisely the same way every time, which requires expensive feeding mechanisms, the robot can see the jumble of items, identify the specific part it needs, figure out its location and orientation, and then calculate how to approach and pick it up correctly. This drastically increases flexibility and reduces the need for upstream automation complexity. 2. Recognizing specific parts that are intermixed with other different objects. This is essential for tasks like sorting items on a recycling line, picking specific components from a mixed kit for assembly, or performing quality control where different product variations might come down the same line. 3. Performing assembly operations that require very precise alignment based on visual feedback. The robot can use its camera to visually guide its end effector into the correct position for intricate tasks, like inserting a tiny pin into a small hole, aligning connectors, or applying sealant along a complex edge, actively compensating for minute variations in part position or fixture tolerance in real time. It allows for much higher precision in less structured environments.
Okay, so vision is about seeing and interpreting. What about touch and proximity? How do robots use those senses to physically interact with their environment and the objects within it?
Right, so moving from sight to touch, tactile sensors provide the robot with the capability to respond to direct contact forces that arise between itself, usually its gripper or end effector, and other objects within its work volume. Tactile sensing can generally be categorized into two main types. First, simple touch sensors. These are often used just to indicate whether contact has been made with an object or not. A basic microswitch embedded in a gripper finger can serve this purpose. It just gives a binary signal, touching or not touching. Potential uses for robots with basic touch sensing capabilities would be in assembly, perhaps for confirming that a part has been seated correctly, performing delicate part alignment where a light touch is needed, or maybe in an inspection tasks for simple gauging is the part there, or basic dimensional measuring activities where contact confirms a dimension. It's like the robot having a simple fingertip, just knowing if it's touching something. Second, more sophisticated stress sensors or force sensors. These are used not just to detect contact, but to actually measure the magnitude of the contact force, and sometimes even the torque being applied. These often employ technologies like strain gauges integrated into the robot's wrist or fingers, or specialized force torque sensors. This allows the robot to know not just if it's touching something, but how hard it's pushing or pulling or how much resistance it's feeling. This capability is absolutely critical for tasks requiring fine motor control, like handling fragile objects without crushing them, performing tasks like grinding or polishing where consistent pressure is needed, or tightening screws or bolts to a very specific torque specification during assembly. Now, proximity sensors, they're slightly different. They're designed to sense when one object is close to another object, but without necessarily making physical contact. On a robot, these sensors are typically located on or near the end effectors, or sometimes on the robot's main body. This non-contact sensing capability can be engineered using various technologies depending on what needs to be detected. Common types include eddy current proximity detectors, which are good at sensing metal objects, optical proximity devices, using infrared light beams like the sensor on an automatic door, magnetic field sensors, ultrasonic sensors, using sound waves like bats, or capacitive sensors. In robotics, proximity sensors might be used simply to indicate the presence or absence of a work part or some other object in the robot's path or workspace, maybe ensuring the gripper is positioned correctly before closing. Crucially, they are also highly useful and increasingly important for safety specifically in preventing injury to human coworkers in collaborative factory settings. A proximity sensor can detect when a person enters the robot's immediate vicinity, prompting the robot to automatically slow down, alter its path, or stop completely, acting as an essential and often invisible safety mechanism.
And the third category was voice sensors. Can robots truly hear and understand us in a conversational way yet? Or is it currently more about recognizing specific predefined commands?
Yeah, voice sensing, or perhaps more accurately, voice programming or voice control, is another exciting and rapidly evolving area of robotics research and application. Currently, it mostly describes the vocal communication of specific commands to the robot or other machines, rather than achieving full natural language conversational understanding like we have between humans. The way it typically works is that the robot controller is equipped with a speech recognition system. This system analyzes the voice input the sound waves of your spoken words and compares the extracted features with a set of stored word patterns or acoustic models representing a predefined vocabulary of commands. When a sufficiently close match is found between the spoken input and one of the stored vocabulary words, like start, stop, pick up, move left, the robot controller then executes the action or sequence of actions that corresponds to that recognized command word. Voice sensors or voice control could be incredibly useful in certain robot programming scenarios, potentially speeding up the procedure, much like voice dictation can speed up typing. Imagine just telling the robot, record this position, instead of fiddling with a teach pendant. It would also be particularly beneficial in especially hazardous working environments, allowing for remote control for performing unique or non-repetitive operations, such as maintenance and repair work inside a dangerous area. The robot could be placed in the hazardous environment, and a human operator, safely outside, could command it step by step using vocal instructions. Move forward slowly, rotate wrist 90 degrees, activate tool, significantly reducing human risk and allowing for immediate, flexible responses without needing to physically re-enter a dangerous zone. So while it's not yet true conversation like talking to HL9000, it's a powerful step towards more natural and efficient human-robot interaction in specific contexts.
Okay, so it's really clear that sensors, vision, touch, proximity, even voice are not just fancy add-ons for robots. They seem absolutely fundamental to how robots can operate safely, effectively, and perhaps most importantly, intelligently and adaptively in increasingly complex and unstructured environments. What are some of the key takeaways then about the overarching importance of sensors for robots as they continue to evolve?
That's a great summary. Sensors are absolutely critical, moving robots beyond being just pre-programmed automatons. They are vital because they provide a way of simulating aliveness, or perhaps more accurately, awareness. They make robots seem more interactive and responsive, moving them beyond purely mechanical, non-reactive devices. Crucially, they give robots environmental awareness. They allow robots to actually understand and react to their surroundings in real time, whether that's avoiding unexpected obstacles, identifying specific objects, or adjusting to variations in parts. They are a vital means of human protection, especially in collaborative robotics. Sensors enable robots to detect and avoid contact with people, which is absolutely crucial for safety in shared workspaces where humans and robots work side by side. They help robots preserve themselves by allowing them to sense obstacles, potential collisions, excessive forces, or unsafe operating conditions. Sensors enable self-preservation behaviors, preventing damage to the robot itself or its tooling. They enable true goal-seeking behavior. With sensors, robots can dynamically adjust their actions based on real-time feedback to achieve a specific objective, even if the environment changes or unexpected elements appear. They're not just following a script, they're actively working towards a goal. They enable that closed-loop interaction with the environment we talked about in control systems. They create that continuous feedback loop where the robot constantly senses the world, compares it to its goal, and acts accordingly based on real-world data, not just assumptions. And ultimately, sensors are what make robots truly interesting, adaptive, and capable of performing tasks far beyond simple, mindless repetition. From an engineering perspective, integrating and interpreting sensor data effectively can make programming challenging in the best possible way. It really pushes the boundaries of what's possible for intelligent machines and leads to constant innovation.
This incredible ability to sense, perceive, and react based on that sensory input leads us directly to the ultimate question, doesn't it? How does all this sophisticated physical capability, the intricate control systems, and this rich sensory perception actually come together to create truly intelligent machines? This is where it gets really interesting, I think. Artificial intelligence. How has AI fundamentally revolutionized the field of robotics, transforming them from mere automatons into genuinely smart, adaptive systems?
The brain of the machine, AI, and robotics.
Yes, this is truly where the magic happens, you could say, where the advanced hardware meets the sophisticated intellect. AI has profoundly, fundamentally revolutionized the field of robotics. It's done this by enabling machines not just to follow instructions, but to perceive their environment, to reason about it, to learn from experience, and to act with ever-increasing levels of autonomy. From dramatically optimizing industrial automation and making factories smarter, to transforming healthcare delivery, AI-powered robots are now significantly improving efficiency, enhancing safety, and boosting productivity across literally dozens of sectors. You could argue that AI is what truly breathes intelligent life into the robot's physical body, unlocking its full potential.
That distinction seems really key. So are robotics and AI essentially the same thing these days? Or should we think of them as distinct but maybe inextricably intertwined fields, each contributing something unique to the equation?
That's a great way to put it. Distinct yet absolutely interdependent fields. They're like the body and the brain. You can't really have one function effectively at this advanced level without the other. Robotics traditionally focuses on designing and building the physical machines capable of performing tasks. The mechanical structure, the manipulators, the sensors, the actuators, the power systems. That's the hardware, the embodiment. AI, on the other hand, provides the intelligence, the software brain, that allows these machines to make decisions based on data, to interpret complex sensor input, like vision, to learn from past successes and failures, to adapt dynamically to new or changing environments, and increasingly to interact meaningfully and naturally with humans. It's this synergy, this tight integration of capable bodies with intelligent brains that has led to the development of the incredibly sophisticated robotic systems we're starting to see now, systems capable of learning, adapting, and evolving their capabilities over time. One cannot achieve its full potential without the other in this modern era. A robot without AI is often just a fancy, limited machine. And AI without a robot or some other form of embodiment is just algorithms running on a server, unable to directly affect the physical world.
Okay, so AI is the brain that perceives, decides, and learns, guiding the robot's actions. What are the core AI technologies then that specifically power modern robots? What's inside that toolkit enabling these advanced capabilities?
There are several key AI technologies that are absolutely integral to modern robotics, each contributing a vital piece to the puzzle of creating intelligent, autonomous operation. Machine learning, ML, is fundamental. This enables robots to learn patterns and behaviors directly from data and improve their performance over time without needing explicit, line-by-line programming for every single possible scenario. Techniques like neural networks, especially deep learning, allow robots to recognize complex patterns in sensor data, like identifying objects in a cluttered scene, process visual inputs from cameras at a high level, predict outcomes based on current conditions and vast amounts of past experiences, and optimize their actions. Computer vision, powered by AI, is paramount, as we discussed with sensors. These systems allow robots not just to capture images, but to truly interpret and analyze those images or video streams. This enables critical functions like precise object detection and recognition, facial recognition, understanding complex spatial relationships for navigation and manipulation, and even identifying subtle defects or anomalies in products during inspection. It's how robots gain a deep understanding of the visual world. Natural language processing, NLP, is becoming increasingly important for interaction. This branch of AI allows robots to understand, interpret, and respond to human speech and written text. This makes human-robot interaction far more seamless, intuitive, and natural, moving beyond simple command recognition towards allowing for more conversational interfaces, easier programming, and better collaboration. Reinforcement learning, RL, is a particularly powerful technique for robotics. It helps robots learn optimal actions or strategies through trial and error, essentially by exploring their environment and receiving feedback in the form of rewards for desired behaviors, like successfully grasping an object, and penalties for undesirable ones, like dropping it or colliding. Similar to how humans or animals learn from experience, RL allows robots to gradually improve their decision-making abilities and master complex skills over time, especially for tasks where explicit programming is difficult, like learning to walk on uneven terrain or performing intricate manipulation sequences. Path planning and navigation algorithms, heavily reliant on AI, are absolutely crucial for mobile robots. These algorithms help robots build maps of their environments, using techniques like SLAM simultaneous localization and mapping, efficiently plan routes while avoiding both static and dynamic obstacles, like other robots or people, and autonomously navigate from one point to another, often optimizing for factors like time, distance, or energy consumption, and sensor fusion. This is where AI truly shines in perception. It intelligently integrates data streams from multiple different sensors simultaneously, like combining information from cameras, LiDAR, laser scanning, radar, sonar, inertial measurement units, IMUs, GPS, and tactile sensors, to create a single, unified, more complete, more accurate, and more robust understanding of the surrounding environment. By combining the strengths and overcoming the weaknesses of individual sensors, the robot gets a much richer and more reliable picture of reality than any single sensor could provide alone. This significantly improves perception, situational awareness, and ultimately the quality and safety of its decision-making, especially in complex, cluttered, or ambiguous conditions.
Wow, that's an incredibly powerful toolkit. It really paints a picture of how AI transforms a robot from a simple machine into something much more capable and adaptive. So bringing it back to the real world, what are some of the most impactful applications of these AI-driven robotics that we're seeing across various industries right now? Where is this making a difference today?
The range of applications is incredibly wide already, and it's expanding rapidly. AI-driven robotics is demonstrating its transformative impact across numerous sectors. In industrial automation, as we touched upon, manufacturing robots equipped with AI go far beyond simple repetition. They can optimize entire production lines dynamically, perform tasks requiring extreme precision with high efficiency, use vision systems to detect subtle defects that humans might miss, predict potential equipment failures before they happen, predictive maintenance, and even collaborate safely and intelligently alongside human workers on the factory floor, adapting their movements to avoid collisions and working as partners. In healthcare and medical robotics, AI-powered robots are revolutionizing patient care in many ways. They assist surgeons in minimally invasive procedures, enhancing precision and dexterity beyond human limits. They aid in patient rehabilitation therapy, providing consistent and personalized exercises. They help with diagnostics by automatically analyzing medical images like X-rays or CT scans. They provide support and companionship in elderly care facilities. And AI-driven prosthetic limbs can now learn and adapt to their users' individual movements and intentions in real time, becoming a truly integrated and responsive part of the person. Autonomous vehicles and drones are perhaps one of the most visible applications. Self-driving cars, delivery drones, and autonomous shuttles rely heavily on AI for complex perception, real-time navigation through traffic, instantaneous obstacle detection and avoidance, and critical decision-making in unpredictable urban environments. AI allows them to adapt safely to constantly changing conditions like traffic flows, pedestrian behavior, road hazards, or poor weather. Service and domestic robots are also becoming increasingly common, integrating AI for smarter operation. Think of smart robotic vacuum cleaners that intelligently map your home and optimize cleaning paths, robotic lawn mowers, and even humanoid assistants designed for retail, hospitality, or household use, performing chores, providing information, and assisting with everyday tasks, aiming to make our lives easier and more convenient. In the defense and security sector, AI-powered robotic systems support military and security operations in dangerous situations. They are used for autonomous surveillance and reconnaissance, for safely disposing of explosive ordnance, bombs, and for operating in environments too hazardous or inaccessible for humans, significantly reducing risk to personnel. In agriculture, agtech, AI robots are helping to optimize farming operations for greater efficiency and sustainability. They can automate tasks like precise planting and seeding, monitor crop health acre by analyzing images from drones or ground robots, identify and selectively remove weeds without herbicides, and precisely harvest ripe produce, leading to better yields, reduced waste of resources like water and fertilizer, and potentially more sustainable farming practices. And in space exploration, autonomous robots, epitomized by NASA's Mars rovers like Curiosity and Perseverance, rely heavily on AI to explore distant planets and moons. AI enables them to navigate challenging terrain autonomously, identify scientifically interesting targets, collect invaluable data, and make independent decisions about their operations in extremely remote locations where direct, real-time human intervention is impossible due to the immense communication delays, light travel time, between Earth and other planets.
It truly sounds like a transformative technology that's reshaping our world on so many different levels, from the factory floor to Mars. But despite these incredible advancements and widespread applications, what are the current challenges? What hurdles does AI and robotics still face on its path towards even wider adoption and more sophisticated capabilities?
That's right. Despite the incredible progress, there are indeed significant hurdles and challenges that the field of AI and robotics is actively working to overcome. These are not trivial issues: data dependence and generalization. AI systems, particularly those based on deep learning, often require absolutely massive amounts of high-quality labeled training data to perform well. Obtaining such data, especially for the vast range of real-world variations, rare events, or unpredictable situations that robots might encounter, can be extremely difficult, expensive, time-consuming, and sometimes even impossible. Furthermore, ensuring that models trained on specific data can generalize well and perform reliably in new, unseen environments or situations remains a major challenge. Domain adaptation, complex decision-making, safety, and explainability. Ensuring that robots make consistently safe, ethical, and reliable decisions, especially in highly complex, dynamic, and unpredictable environments where pre-programmed rules might not cover every eventuality, remains a major research focus. How do you guarantee safety when the AI is learning and adapting? Furthermore, the black box nature of many advanced AI models makes it very difficult for humans to understand why a robot made a particular decision. This lack of explainability is a significant barrier to trust, debugging, certification, and establishing accountability. Energy efficiency and computational cost. AI computations, especially deep learning inference and training, demand significant processing power. This translates directly into high energy consumption. This profoundly impacts the battery life, operational duration, and practicality of mobile robots, which need to operate untethered for extended periods without frequent recharging. There's a constant trade-off between the sophistication of the AI intelligence and the robot's endurance and cost. Safety, security, and robustness, preventing malfunctions due to software bugs, hardware failures, or unexpected sensor readings is critical. Additionally, protecting robots against malicious hacking or adversarial attacks, for example, tricking a vision system, is becoming increasingly important as robots become more connected and autonomous. Avoiding unintended or harmful consequences resulting from complex AI interactions is absolutely crucial for widespread public acceptance and trust. Ensuring these systems are robust against both accidental failures and deliberate attacks is paramount. Regulatory frameworks and ethical concerns. The widespread deployment of AI and robotics raises broad and complex societal questions that we are still grappling with. These include serious concerns about potential job displacement in certain sectors, privacy implications as robots equipped with sensors collect ever more data about their surroundings and human interactions, and the difficult challenge of establishing clear legal and moral accountability when an autonomous robot causes harm or makes a mistake. Who is responsible? These complex issues require careful societal discussion, proactive policy development, and ethical considerations embedded directly into the design process.
These are undeniably big, important questions for the future, touching on technology, society, and ethics. So, looking ahead, weaving together these challenges and the relentless pace of technological progress, what does the future of AI and robotics realistically look like? What are the key trends we should expect to see?
It's a dynamic field, but as AI continues its rapid, almost exponential evolution, the future of robotics looks incredibly promising, poised to push the boundaries of what machines can do even further. Key trends we anticipate seeing include Increased and deeper human-robot collaboration, HRC. AI will significantly enhance robots' ability not just to work near humans, but to work with humans safely and effectively in highly dynamic shared environments. This means moving beyond simple coexistence, where robots stop if humans get too close, towards true partnership, where robots can dynamically adapt their actions based on human movements, predict human intentions, communicate more intuitively, and seamlessly integrate into human workflows, making collaborative tasks safer, more fluid, and more efficient. Advancements towards more general AI and embodied intelligence. While true artificial general intelligence, AGI, is still likely a long way off, future robots will likely possess more generalized intelligence compared to today's highly specialized systems. This could enable them to handle a broader and more varied range of tasks and adapt to entirely new situations with less explicit retraining. This idea of embodied intelligence, where the AI learns to leverage the robot's physical body and senses more effectively to understand and interact with the physical world, will be key. Improved autonomy, adaptability, and learning. AI will continue to drive robots towards operating with even greater independence in dynamic, unstructured, and changing environments, requiring minimal human intervention for increasingly complex tasks. This means robots will become better at handling uncertainty, learning continuously from new experiences in the real world, lifelong learning, and adapting their behaviors on the fly without needing constant reprogramming. Deeper integration with the Internet of Things, IoT, and cloud robotics. AI-powered robots will become increasingly interconnected, not just with each other, but with a vast network of other smart devices, sensors, and cloud computing platforms. They will share data, learn collaboratively, and access powerful AI models and knowledge bases from the cloud, leading to more intelligent, coordinated, and context-aware robotic systems. Robots will be active participants in a larger, aware digital ecosystem, emphasis on ethical AI frameworks and responsible deployment. As AI capabilities grow, researchers, policymakers, industry leaders, and engineers will increasingly focus on developing and implementing robust ethical guidelines, standards, and regulatory frameworks. This is essential to ensure the responsible, fair, transparent, and beneficial deployment of AI in robotics. It involves proactively addressing concerns like bias in AI decision-making, ensuring fairness, enhancing transparency and explainability, and establishing clear lines of accountability from the outset, aiming to build public trust alongside technological capability.
It's absolutely clear we're only at the very beginning of this profound technological revolution, and the future promises machines that are not just automated, but truly intelligent, adaptive, and integrated into our world in ways we're only starting to imagine. Outro. Wow, okay. What a truly deep dive that was into the intricate world of automation and robotics. We've journeyed from understanding the fundamental structure of a simple robot arm all the way to grappling with the complex capabilities and profound ethical dilemmas surrounding artificial intelligence in these systems. We've explored how these incredible machines are designed, how they're precisely controlled, and how they're being applied across nearly every facet of our modern lives. We've seen how they tirelessly take on dangerous tasks, bring unparalleled precision to manufacturing floors, and are increasingly becoming partners, assistants, even companions in our daily lives, all driven by sophisticated control systems and the ever-evolving power of artificial intelligence.
We really have just scratched the surface, haven't we? When you think about the layers involved, from the simple, almost binary logic of something like a bang-bang controller, all the way up to the elegant, complex mathematics of quaternions that allow robots to navigate and understand rotation in 3D space without getting lost or confused. It's truly a field built on layers upon layers of brilliant engineering, clever mathematics, and groundbreaking scientific insight. It's constantly pushing the boundaries of what machines can perceive, understand, and achieve.
So as you go about your day now, maybe you'll see a robotic arm assembling a car on a documentary. Or perhaps notice your own smart vacuum cleaner intelligently navigating around furniture in your home. Take a moment and think about this. If robots are becoming ever more autonomous, increasingly capable, and more deeply integrated into our world every single day, what are the next kinds of problems, the next grand challenges that we will ask them to solve? And perhaps just as importantly, what new ways might we as humans and as a society need to adapt, learn, and evolve alongside them to truly unlock their vast potential for the benefit of humanity?
That's a truly provocative thought to end on, isn't it? And it really highlights that constant dynamic interplay between technological advancement and human society. The ongoing story of automation and robotics isn't just about the machines. It's profoundly about us, our choices, and the future we want to build together.
That's all the time we have for this deep dive. We sincerely hope you've gained a clearer, richer, and perhaps more insightful understanding of this vital and rapidly evolving field. Until next time, keep learning, keep questioning, and keep exploring.